All right, so let's bring that information that we had about increasing and decreasing intervals together with that critical value definition. So we get another piece of information here. When our first derivative is greater than or equal to 0, it's added the equal to so that we could include those endpoints, we can say that our function is increasing on that interval. And if it's less than 0, well, it's decreasing. And this makes sense if you think about the slope at a point, right? If our slope at a point is greater than 0, it's positive slope, our function would be increasing. And then if we want to find these intervals of increasing or decreasing, there's a series of steps that could help us do that. We would want our first derivative. We'd want to find those critical values because those are the places where our sign could change because we're either at a corner, at a vertical asymptote, right, an infinite discontinuity, or we're at what we will call a local or relative extrema. And then we're going to create our sign chart for that first derivative using that sign chart to determine our intervals of increasing or decreasing. And then, of course, pay close attention to what you've been given. If you already have the first derivative, whether in a graph or elsewhere, do not take a first derivative, right? You already have it. So we'll see both of those examples as we move forward with a couple of things. All right, so the way we must typically see this and why I spent so long on polynomials and rationals in that week 1 of our course is with polynomial functions. So if we're going to figure out the intervals where this polynomial is increasing and decreasing, we could follow those sort of steps given above. Let's go ahead and find our first derivative. So our first derivative, nice, just power rules. So we're really not focusing on how hard it is to take a derivative and more focusing on our understanding of how those derivatives are related to these intervals of increasing and decreasing. Then it says, okay, well, we need to figure out our critical values. So we need to think about when is this, right? So that was our step 1. If we write down steps, I don't really love it, but it's okay. Step 2 is to say, well, when is this equal to 0 or undefined? Now this is just a linear function, so there's really no reason to be talking about undefined. That's never going to happen here, but it can equal 0. Very straightforward solve there. Our critical values are, ooh, I can spell. Critical value, there's only one, and it was when x is equal to 3/2. Boom. So you could solve that set equals 0. Right? This is just going to be our x-intercept of our function, our derivative function. And so then our last step is to make that sign chart. Now, of course, this is a very underwhelming sign chart, but we could go ahead and write it. 3/2 is our particular critical value. Go ahead and just put a little dot there. And we need to figure out what's happening with our line around that value. So if we look back at our first derivative, that is a linear function, positive slope. So it does something like this. We know it is negative up until that 0, and then it will become positive as it crosses the x-axis because of that positive slope, right? We know the end behavior of technically a polynomial with an odd degree and a positive leading coefficient. So we've got this, and now we can use that to talk about our intervals of increasing, oops, I meant to, and increasing and decreasing. All right, so our interval of increasing is anywhere that our first derivative was positive. Our interval of decreasing is anywhere that our first derivative was negative. And so we got increasing on, and then that is going to be 3/2 to infinity. And it's decreasing on negative infinity up to that halves. I know it will never cease to be bananas to me that I'm using a hard bracket, that I'm including 3/2 in both the intervals of increasing and decreasing. But I'm gonna go with the arguments that I've read that say we should include this. But again, if you are really opposed to it, that's fine. Um, I know many smart people who also believe that it should be an open interval. So your choice on that. So there you go. That's our intervals of increasing, decreasing. We might as well, since we're here, let's pull up Desmos and look at this graph to sort of see what we see. This also should not be that surprising if you think about the original function. This original function is just a parabola that is opening upward. So it would start decreasing and then it would go to increasing. But let's just see x squared minus 3x minus 21. And so we can see There's our vertex at 1.5 or 3/2. And as you can see, we have a decreasing side, right? Everything, let me just go ahead and grab this guy. We are decreasing on this parabola, boom, up until that vertex, and then we are increasing. So that's exactly what we're finding. Obviously, with something as simple as a quadratic, we could have found this just knowing about our quadratic and the fact that our vertex was a minimum and sort of knowing where that vertex was, that negative b over 2a shortcut. But here's the calculus-y version of that so we could see the steps.